Well, thank you for the presentation. I'm Federico. I'm presenting MAIZX, which is a framework for carbon awareness in cloud computing. My background is in electronic engineering. Also, I did my master's degree in computer science, specialized in cloud computing and network infrastructures. And I also lead a startup in the field of sustainable cloud computing. So together with Ernst and Sven-Arne, they work at Simula. They led my research through my master's degree, and I'm presenting here an extension of the potential of this framework into the real world. So let me see. Okay, so pretty much, we know how cloud computing is, how important it is, and the real question here is like, we all want to run cloud computing on renewable energy, but we kind of know that it's not possible fully %. So it's about an optimization problem that we have, and that's one of the motivations behind this. Even if we produce like enough renewable energy until 2040, I think, carbon emissions from cloud computing are going to be so big that they're going to account for 40% of the total emissions. So it's a matter of how we're going to organize the whole thing in a better way to make the best use of energy. There's a lot of saying about public cloud and then how 70% of the market is controlled by hyperscalers like Amazon, Microsoft, and Google, but no one's talking about private clouds. So part of the motivation of this research is how can we deploy this in private clouds and make private clouds more efficient in multi-cloud environments. So yeah, let me present you first the MAIZ framework. MAIZX stands for moving all into zone X, which means moving computing loads, no matter which computing load, into a different zone. And the X zone is the most efficient zone, we could say. At the higher level, the MAIZX framework works together with an API that, in this case, we use electricity maps to get the carbon intensity of each region in different countries. And then it works together with the hypervisor, telling the hypervisor the ranking for each of the nodes that we're having in this cloud. So that's the pretty much the higher level of the MAIZX. The ranking algorithm uses a carbon footprint of each node, forecasted carbon footprint of each node, and also it takes into consideration computing power. How much power are we using? How much power we have used in the past, and how much power we're forecasting to use. And also very important for private clouds, because all the clouds are different, is the schedule weight. Do we need this load right now? Do we need it in the future? Can we like wait until 2 weeks into the future? So this is pretty much it's a linear algorithm, but it provides a lot of flexibility for private cloud operators. The methodology that we use to develop this framework and also to get the results, we deployed 3 different nodes in Europe, specifically because Europe has a high density of data centers. So we have the flexibility to move things around. We use real data centers for this case scenario. We use Equinix, which is one of the major data center providers, also provide data centers for the hyperscalers. So we are comparing to a real cloud, public cloud operation here. We use, then with the results from the implementation, we simulated this scenario into the year 2022, using the carbon intensity data from year 22 and assuming the same load through the whole year to make different types of experimentation. Here's a high level of how it works. The cloud, well, for those who don't know how the hypervisor works, Well, at least in this case, we use Open Nebula, which allows to integrate edge nodes, edge computing nodes, on-premise data centers, and also public clouds. So the idea of using Open Nebula was to, okay, can we scale this to multi-cloud environments or hybrid cloud environments? And yeah, this is how it works, the Open Nebula. And then we use combination of the same metal servers in all the nodes in Spain. For this experiment, we use Spain, Germany, and Netherlands together. Sorry. The methodology was calculating the carbon footprint of each node, putting everything into the ranking algorithm, and then ranking the nodes as they were like working with the loads. I really like this. This is the simulated carbon intensity through all the year. So from all the year 2022, there were like 12 days where the Netherlands had the carbon intensity at the lowest. So this is to give you an idea how the algorithm could work in this simulation, right? And then these are the results. We use a baseline scenario where I'm going to go back a little bit just to give you an idea what the load was. We use a load of 50 virtual servers, all containing WordPress websites. And this was specifically picked because, WordPress is like 80% of the websites in the world. And then it's like the minimum example we could use to do load shifting or apply a framework like this. This could be, of course, used in AI or like other types of applications. So the baseline scenario is the hypervisor working without no interference through all the year. Scenario A, it's we picked always the node with the best ranking, and then we achieve like 2.50% reduction. And is a scenario B and a scenario C is what becomes interesting. It's like we figure out, and then I think in previous talks they talk about this, is let's shut it off. Let's shut the rest of the nodes off while we pick which node is being used. So this is a scenario B. So moving things around and shift them, we achieve 85% carbon reduction. And then a scenario C is, no, sorry. This is a scenario B, just the ranking, and then doing load shifting in real life, like in real time, we achieve a little bit higher carbon reduction. So the purpose of me presenting this here is to not actually just presenting a framework, but to show you the potential of this framework into the high level, into our like targets for 2040, right? So if we apply this 85% of carbon reduction to only 1% of the targets of ICT, data-driven climate change and monitoring solutions, and also apply that to ICT data processing, hosting, and related activities, we could achieve. This is an assumption. So this is the theoretical calculation of the energy. We can, if we shift 27 million computing loads using this approach, we can achieve like we can even like how do you say, like we can estimate to remove like equal to 2.44 million cars, removing them out of the earth. The way this works, this is the it's called impact forecast tool, and the way it works, it's we calculate how much energy we use from the real world, like real energy, like gray energy, how much energy we're going to be shifting in this whole year, and then in that sense we can calculate the carbon performance potential. I wanted to introduce this CPP because I'm in the entrepreneurial world. I've been trying to reach some of the impact funds and then they're using this as a metric. So it's very important for us in the scientific world to have like some kind of measurement that we can estimate how much carbon we're gonna save into the future. So some discussions here. Yeah, every multi-cloud environment have like different approaches and different methodologies or different business needs. So it's important to have flexibility in the algorithms or in the carbon loading, in the carbon balancing that we're having. We found some really interesting ways to do carbon tax, ESG reporting, and also some kind of frameworks that are needed in the commercial world. And yeah, I would like to open the question, do we really need to operate in the same way that we're doing it, or we can move things to countries where they have more clean energy, such Canada, the Nordics, or in Latin America, Costa Rica, for example. So yeah, thanks a lot for the presentation, for the time. Thank you.
Federico?
Yeah.
We have a couple of minutes for questions. Is there a question for Federico? In the room or online? See in the room question right away.
Yeah, thank you. So I'm confused a little bit. So are you migrating whole VMs?
Yes, that's correct.
You're still claiming a net gain after migrating whole operating systems?
Yeah. Well, what's your name? I'm sorry.
Adrian.
Adrian. Adrian is asking if we are migrating whole VMs in real time, right? That's the question. Okay, yes, we're migrating whole VMs in real time. The hypervisor does that. So we are interfering with the hypervisor. This framework, I wanted to like target one specific part of the cloud that could work in any cloud. So this could work with VMware, with OpenStack, with OpenNebula. It's just like changing the way the decisions are made at the hypervisor level.
So you're accounting for the footprint of moving all that data, and what about the
Good.
performance waiting for your VMs?
Okay. Well, he's re-asking if we are counting with all the network traffic and all that. That was one part of the research that was not covered. It's very good point because the network traffic needs to be considered. There's also a footprint there. And I would love to explore more that in further research. But yeah, thank you for addressing that. Yeah.
We do have an online question, if it's okay.
Yes.
So I have a question. Have you considered other factors beside own energy consumption, for example, water usage efficiency or increased energy demand to cool data centers after moving tasks?
Okay, yeah, thank you for the question. Yeah, in the research, the experimentation level, we experimented with top tier data centers, Equinix data centers. They provide power user effectiveness to the users, right? So we have that behind some metrics are being considered, but in the real world, private clouds are a combination of edge computing devices, on-premise services, the NAS server from our other exposer, for example. So we didn't consider any of the data center layers. It's just a framework that applies to the logical layer, abstraction layer from the hardware to the top. Yeah, and then considering only energy of each region. I hope that answers your question.